Today we will talk about compression technique, what is the data compression, lossy compression, and lossless compression. And at the end, at the second part, we will talk about this method. This is which we should review about the parts and algorithm that how it's work and like that. As I tell you, we are finished this part and we are with the image compression. This part, this just morphological process is remain from our subject, and some part maybe about the object recognition. That we can then following and see all the uh, image processing aspect and finish it. The compression technique, as we say, are broadly can be classified into two parts. One is lossless compression, and another one is lossy compression. And with the lossless compression technique, we can see reconstruction is possible, and there are some variable length coding, LZW coding, deep plan coding, and predictable coding, DPCM part. That these are the methods that can be higher on this uh, part of the techniques. And we can say the lossy compression technique is compression technique that where perfect or lossless reconstruction is not possible. Within this method, you can have the transform coding, wavelet coding, basic of image compression standard like JPEG, and basic of vector quantization like MPEG part. Uh, these techniques, I mean the compression techniques, are lossless, means that the image compression is a compression algorithm that allows the original image to be perfectly reconstructed from the original data. And on the other part, the lossy data, or in the other words, lossy image, can be the image compression, is a type of the compression where a certain amount of information is discarded, which means that some data are lost and hence the image cannot be decompressed within 100% originally. These are the two methods that we have in data compression. And compression techniques are broadly classified into two parts. One is the lossless compression, another one is lossy compression. Which, if we want to review again, we can say that various methods are there, especially in the lossy techniques. This slide is repeated, but no problem. We have the compression where reconstruction is not possible, but in the lossless one, it's possible. First, broad and highlighted point is this. Another thing is that here in lossy compression, you have transform coding, wavelet coding, basic of image compression standard like JPEG, and vector quantization like MPEG part. Uh, More things that I found from one recent article is something like that, because I was searching for some recent method also to inform about them for you. Is first is this about lossy. We have fractional coding, lossy predictive vector, like coding DCT and DWT, and lossless part is the lossless predictive coding, local PPWT, variable basic size segmentation. Uh, and if we want to go more detail, even each method that is here means that it's written there. It can also have some categorized with more detail, something like hover FIC, region-based fractal image using heuristic search, fractional taking based on human vision, using genetic algorithms, DCT lunar product, and fractional image with classification scheme. These are with the fractal image compression, and DCT is suppose can be again categorized with this method of spectral similarity strategy, 3D discrete cosine transform, and wrap discrete cosine transform. These are the more detail about the methods. Just I want to inform you that there are lots of methods that can work in that. Suppose for coding a wavelet itself, you have lots of methods like that: embedded zero, wavelet compression, predictive embedded zero again, wavelet based embedded comparison. You see, so many methods are introduced recently, and this part of knowledge or science, it's become more and more deep as you can see here. Uh, Again, if we want to see the lossless image compression part, there are with variable block size, dynamic image data in a spatial and temporal domain, local and lossless image compression using gap and Burroughs Waveler transform, lossless compression, algorithm based on texture and multiple temper, and 3D losses methods based on region growing. Again, suppose we have some methods which are related to fuzzy algorithm, something like fuzzy vector quantization and fuzzy algorithm for learning vector quantization. You see that there are lots of methods that can help us to do this job, and these especially this lecture can be about more than 2 or 3 maybe semester to talk. That is why maybe we are not going much more deep to some methods, because and we will have some introduction about them, and somehow maybe some elementary part that we can do with the help of MATLAB software and do some activity based on that. Uh, Um, these are as I said, these are the methods that can be worked, and these are some other methods that hire. Some of them even it's not mentioned in your book, as I found in some recent paper, and some of them maybe are uh, have some brief about them in your book. Anyway, the methods that we describe, then we will have for our exam and for further study, is that the parts that we have in the book don't have uh, much more tension about learning, or but be aware that there are lots of methods and work that we can do for these techniques. Let us again review what is data compression, which is the process of dimensioning the S-tray size of any data or file so that it consumes less space on the disk. And it is technique for modifying, restructuring, encoding, and converting schema or instance of any data to reduce its size. That is not new. Last lecture also we talked about it. But in simple word, it's converting the file in such a way that its size is reduced to the maximum extent, and data compression is also known as bitrate reduction or source coding, something like that. We can have some scheme or some block diagram like this, which you can start from original image. You can have data redundancy reduction, coding part, and then transmission, archiving, decoding, and reconstruction. And after that, you can have the reconstructed image. As an example, an image that is converted or compressed to reduce its size without losing the ability to reconstruct the image. Now, the question here is why there is the need for data compression. That, as we said, there are two primary reasons. There are more, but more highlighted one is first is storage, which means it's help in reducing the size of the data that is required to store it on the disk. And time is saves time in data transmission as the size is reduced to an extent. Um, these are the two main reasons that we should have this data compression. More detail about logic compression we'll have in this lecture, and then we will have the technique in the second part. First is that we can say lossy compression is the method that involves the elimination of some specific amount of data. This method can help to reduce the file size to some great extent without any noticeable things, which is more important for us. And also, once the file is compressed, it cannot be restored back to its original form as the data from the file is significantly reduced. These techniques is much more useful when the quality of the file is not essential, and additionally it helps to save much space on the disk to store the data. Lossy compression is not useful when the quality of the file is somehow essential. And besides, if there is any further analysis to be processed on the record, this method is not ideal. This method is generally used for audio and video. Remember this part. And where there is some significant amount of the data is lost and even uses cannot recognize it. User cannot recognize it. Remember these two more points, which is the first one is it's higher on the audio and video, and second is that there is the significant amount of the data which is lost, and even users cannot recognize it. Uh, some example of the lossy compression will be this Lena photo that you will see at the left shows the black artigraph compared to the original one as the result of JPEG compression, which is used, and you will see, I don't know how much is visible from your side. Right side and left side, there are some different and some, we can say, corruption here and even here from this photo. And then you will see the act of these methods. The other methods that we had, as we discussed, that was lossless compression, which it's again the technique that involves only the certain amount of elimination of data. And this technique also help in reducing the file size, but not to the greater extent as that of lossy compression. Instead, in this method, if the file is compressed, it can be restored back to its original form. Further, the quality of the data is not compromised, hence the reduction in the size is not much. This is the one point in this method. And remember that lossless compression is not useful when you want to reduce the size of the extra storage. Also, if there is any further analysis to be performed on the file, lossless compression also is not beneficial. This is one more points or more highlighted things that you should remember. Uh, on the other way, it's useful for maintaining the originality of the files by eliminating only the unwanted data. And this technique is commonly used for text file, sensitive documents, and confidential information. See, suppose the original image is the left, is the identical to the compressed right one. This is the right one in the PNG and DICOM part. It's represented by some identical graphs at the bottom that shows the gray value for the pixel in each column is the same between two images. You will see the uh, quality are not much more change. Even the main image is compressed, which is it's a great work. You can reduce the size, and also on the way, if you reduce the size of the data, you can reduce the time for evaluating that, which is more important during for analysis of further analysis of the work. This is the PNG image that they made from the main image here. This is the main aim that maybe we can conclude from this lossy and lossless compression, and we can compare them here. Means that the main definition between them is that lossy compression it's involved the elimination of a specific amount of data and it helps to reducing the file size to some great extent without any noticeable things. But lossless compression is the technique that involves only the certain amount of elimination of data. And this technique also helps in reducing the file size, but not to greater extent. Compression ratio in lossy is high, which is in lossless is low. File quality is low, which is in lossless compression, it's again low. File quality in lossy compression is low, which is in lossless is high. Elimination of data, even in lossy, is that even the necessary data is allowed remove, which is not noticeable. And in the lossless compression, only some specific amount of unwanted data will remove. Restoration in lossy compression is that it cannot restore its original form, but in lossless compression, it can restore its original form. In lossy compression, loss of information is that it's involves some loss of information. The technique does not include any lossy information in lossless form. Data accommodation in lossy compression is that more data accommodation we have, but in lossless compression we have less data accommodation. Distortion in lossy compression is that file will be distorted, but in lossy compression is not distorted. Data holding capacity it's in more in lossy compression, which in lossless compression it's less. And some algorithm method which use in lossy is some transform coding, DCT, DWT, fractal computing, RSSMS, which in lossless we have other something like Hoffman coding that today we will see that. We have Schuan Farong coding and arithmetic, arithmetic encoding that you can see in lossless compression. File types in lossy compression is JPEG, GIF, MP3, M4, MKV, and OGG, as you can see. And lossless one, it's RAW, BMP, PNG, and WAV. Now maybe you will see that when you will convert your image in your computer to the BMP or PNG, then what we can see for the other parts of or other parts of the image type. Suppose now when you will convert to the JPG, JPEG, JPEG or GIF or MP3 or MP4 parts. Now maybe it's become more broad in your mind that which methods will happen that you have the different format of the image and the type of the image when you will convert exactly which type of the techniques will be used in that. Um, but maybe one problem will arise in your mind that which methods or which of them we should use. Suppose PNP is better or JPEG, or MP3 is better or other form of the storing data or format of the data. Which one is uh, may be useful for us? And here I try to give you some hints through that all those both of them are data compression. Each can be useful under some different condition. Suppose lossy compression can helps in reducing the file size. Then it means that it's helpful to those who haven't vast amount of the data stored on the database. So this technique is useful is in storing the data with a much dimension size. Also, for web page files, for such lower size is beneficial for faster loading. Further, this process doesn't allow any after analysis of the data once compression is completed. Also, the file cannot be restricted in its original form as it involves the losses of data. Unlike the lossy compression, the lossless compression does not involve any loss of data, means that you don't have any loss of data. Neither the quality of the data is compressed, nor the size of the data is excessively reduced. It keeps the original format so it can be stored and further operation can be performed. This method is helpful for those who needs to access the data back again without compressing its quality. These are the two highlighted things that I wanted you review, and then compare with the previous data. Then with the losses, if you have the BMP and PNG and WAV support, what will be different between JPG and GIF and MP3 in whole? You can compare through these slides. Some final things that for first part of today's lecture, I want to review with you that is that lossy compression and lossless compression will help in compression of data in their unique way. And while lossy compression is useful to store the data by compromising the data, lossless compression doesn't. And lossless compression technique is beneficial for maintaining the originality of the data, and lossy compression, on the other hand, doesn't. Both these methods are helpful in database management, then to identify and compress the file accordingly. It's okay for first part of our today lecture. For second part, we are going for the comparison model and some technique that we will review uh, after some rest that we have. We talk about the compression and compression method, and fully we understand what is the lossy and lossless methods, different formats that was essential for today's lecture. Now, let us see the model for the compression, how we can do that. As we talk also, we know the image as the array of x and y, means the 2D imagination about the photo or image. We should have some reduced data redundancy as the source encoder. After that, we should increase the noise immunity with the channel encoder. Then through the channel, we have some noise. And then we can have channel decoder and source decoder to again have f prime xy. What the difference between fxy and f prime xy is that the output from this block can be something like the uh, compressed one. And we will monitor the difference between the original one and compressed one as the two samples that we will see. This model, they connect channel, encoder, and decoder. There are some source encoder model also, which in that you have the raw image data which will be entered to the mapper or reduce interpixel redundancy. And then you have some quantizer, which reduce the psycho-visual redundancy. We talk about psycho-visual redundancy. Then you have the symbol encoder, which reduce the coding redundancy and sequence of encode symbol. You have other way will be the sequence of encoded, then symbol decoder, and then inverse mapper and raw image data will come out as the two-way or two-way road from the compressed one to the original one to compress and compressed one to the original or decoded one model. We can have this, but and basic compression methods are something like these methods, something like Huffman coding, Coulomb coding, arithmetic coding, LZ, W coding, run length, symbol based, bit plan. Um, all of them maybe we will not consider. As I show you, there are lots of more methods here, but I will try to bring some talk for you about the at least difference between them and you will understand them better. Otherwise, more theoretical part from this part needs more than our syllabus, but the portion that we promise at the first day, definitely we will do. Let us then do the Hoffman coding as one of the famous methods for which work based on JPEG image compression. You know, this method was invented from the David Hoffman in 1952 when he was the graduate student of MIT and developed this algorithm for lossless compression. Why we say lossless? Because the format is JPEG. Okay, and maybe it's nice that you know it's from his school work means that maybe from this period of time you also can find some nice method and his algorithm known as Hoffman coding. In that it can be used to compress all sort of the data and it's an entropy based algorithm that relies on an analysis of frequency of symbol in an array. And this method can be demonstrated most vividly compressing a raster image. Uh, okay, let us see in detail what is that. This part I bring from some white uh, article, which was about the Hoffman coding, and it's not from your book. But at the end, I will explain the example that you had from your book. Maybe I feel that with this description that they add inside their article, it may be more clear for you. Even at the end of today, at the reference, as usual, I put this reference that you can read even the main article. But the main part of that I bring for my PPT. You know, think that we have some 5 by 5 raster image, 5, 1, 2, 3, 4, 5 at the row and 5 at the column. We have this is my image, which this image is 8-bit and it has 256 different color then and some arrangement like this photo that we have. Hmm? Then the uncompressed image, if we want to store it for our memory, you know that we have 5 row, 5 column, 8-bit. It's become 200 bits of storage to just take and store this uh, image inside of my memory. If we want to use the Huffman coding, first we count of how many times each colors occurs in the image. Suppose how many white we have in this image? 40 times uh, white, 6 times black, and 3 times red, and 2 times blue. Then we sort the colors in order to decreasing the frequency. Means that sorting from the low to high, like that. And we have something like this: 14, 6, 33, 2. And now we put the color together by building a tree such that the color forest from the roots are least frequent. Okay. Then the color are joined in pairs with the node forming in the connection. A node can connect either to another nodes or to the color. And in our example, tree might look like the things that we have. Okay. The figure like this we can have, and we have the relation between them like this. Let us go more. Result, it shows that we have the white color for the frequent of 14, black for 6, red for 3, and blue for 2. Then this can be in the bit code, something like this, that it can be used for encoding and decoding. Each color is encoding as follow. We create the codes by moving them the roots of the tree to each color. If we turn right at nodes, we write 1, and if we turn left, we have the 0. This process will yield the Huffman codes table in which each symbol is assigned the bit codes such that the most frequent occur symbols had the shortest code, while the least common symbol is the longest code. You will see 2 and uh, for means that blue and white as the frequent of 2 and 40. The bit code difference is something like this. Um, then the main aim of this coding is that the most repeated one has the less code, and least repeated color will be the big code at the end. Then the Huffman tree and the code table is not the only possible. We can have some different one, and alternative trees also we can have for this. Suppose for 2 you can also have the 11 based on this uh, image. The corresponding code table then with the maybe the another formats of this Hoffman coding can be something like this with the new methods. And using the variant is preferable in our example. This is because it provides the better comparison for our specific image that we have. Um, Let us see once more or more detail about this Hoffman coding. You know that because each color in these methods has the unique code that is not prefixed to any other, the color can be replaced by the bit codes in the image file. The most frequently occurring colors, white, will be represented with just a single bit rather than 8 bit. Black will take 2 bits, red 1, red and blue will take 3. And after this replacement, all the 200-bit image will be compromised by something like this: 14 multiplied by 1, 6 by 2, 3 by 3, 2 by 3. It's become 41 bits. Then about 5 bits to compress to 25 bytes in original image, we have the difference. Of course, if we want to decode the image, the compressed file must include some code table. We need to understand what is the relation between them, which takes up some space, and each bit code derived from the Huffman tree unambiguously identifies the color, so the compression loses no information. This compression technique is used broadly to encode some music, image, and certain communication protocol. Typically, the um, variation of algorithm is used to improve efficiency, and the method is described is generally part of some general compression algorithm such as flat zip or image for image that they call it LAC. Remember this point that lossless JPEG compression use the Hoffman algorithm in its pure form, and lossless JPEG is common in medicine as a part of DICOM standard, which is supported by the major medical equipment, this DICOM output, and the manufacturer will do that, especially for the work on MRI photos. They will use that, and variation of laws of JPEG algorithm are also used in the raw format, which is popular among the photo methods because it saves the data from cameras, image sensors without losing the information. That was very brief. Now again, we will come back for one more review about this stat. Think that we have A1, A2, A3, A4 as the color. And now we want to see the original source and source reduction just about the image that we have. Think that probability of A2 is something like zero point 0.4, A6 is around zero point 0.3, A1 zero point 0.1, A4 zero point 0.1, A3 zero point 0.06, 85 is 0.04. Then from that, we can start from A3 to A4, A3 and A5 with the source reduction sequence, which is that the first sequence, if you want to see, this A3 and A5 can be add and it's become zero point 0.1. Then zero point 0.1 and zero point 0.1 of A3 and A3 can add and it can become zero point 0.2. Then zero point 0.2 and zero point 0.1 can add and it's become zero point 0.3. Then zero point 0.3 and zero point 0.3 can come as the last stage and it's become zero point 0.6. This source reduction can come and also can compress our image. Let us see more like this. Suppose the symbol of A2 probability is zero point 0.1, we will give the code 1, and A5 as the last one, which has the last, means that the less amount of the data, it will give the bigger codes for that. And then through this sequence, one by one, we will try to compromise it. We have one thing that we call it efficiency as the formula, which through that you can calculate the L average or average length and ratio with the number of bits that you have, and you can calculate the Hoffman coding's ratio through that. Thing is that in Hoffman coding, each symbol is encoded with different code lengths and coding redundancy is removed. Hoffman coding is the most popular variable length coding techniques, and this coding involves two steps. One is that to create the series of source reduction by ordering the probabilities of symbols under the consideration and combination the lowest probability symbols into the single symbols that replace them in the next source reduction. Second step is that to code each reduced source starting with the smallest source and working back to the original source. The Huffman coding encodes the source such that the lowest the probability of symbols is the largest is the code length and vice versa as we review. Some example, more example, suppose encode the following source using the Huffman codes with this probability of suppose A1, zero point 0.1, A2, A3, A4, A5, and A6. What we should do? First, we should arrange the source symbol in the descending order. Okay, from the high to low, we will order. The symbol will be changed as we show here, and then create the series of reduction source by combining the lowest two probability. See, suppose for the first stage, as already we show, lowest probability is about zero point 0.6 and zero point 0.4. Then we will add them together and we will create the 0.1. Then again, For the second step, we will have lowest probability of zero point 0.1. We just take the last two, add them together, it's become zero point 0.2. For stage 3, we have the least probability of zero point 0.1 and zero point 0.2. We will add together, which become zero point 0.3. And at the end, just last zero point 0.3 will remain. We will add them together and it's become zero point 0.7. This creation series will be continued until a reductor source with only two symbols is there. You will go till the stage that you just have two uh, point or two number. This is the reduction method. And quote each reduction reduce source starting with the smallest source and working back to the original one means that from the back from the step 4 also we can come back and regenerate. Suppose zero point 0.6 can be the summation of zero point 0.3, then we will give the codes for them. Here if you see from stage 4, the biggest one we will put 4 1 and lowest one we will put 0, then again we will come back, one numbers will generate till the end of the process, which you can have the code and you will have the probability and you will have the symbol that you will generate. Then this Hoffman coding is some interesting properties of that we can review is that one is that after the coding procedure is accomplished, the source symbols is encoded or decoded one at a time with the lookup table. And this is block code because each source symbols is coded into the fixed sequence of code symbols. This is instantaneous because each code's word in a strings of code symbols can be decoded without referencing the succeeding symbols. This is uniquely decodable because any strings of code symbols can be decoded in only one way. One more example, you can see given a string of source symbol of A5, A3, and A4 that we have. Here, first we'll give the codes for that bigger to the end, and then we know the combination of A5, A3, and A4 as the codes that we assign for them, and then we can decode them in the vice versa. There are some other optimal variable late coding techniques that maybe we can have some a small talk about them that they call it truncated Hoffman codes, which is only most probable case symbols of source are encoded. There is some B codes, which each code word is made up by continuation bits and information bits. The continuation bits separate individual codes word by alternating between 0 and 1 for successive symbols in the string. This coding is optimal if symbol probability have the relation that we given here. Shift codes is also other optimal technique for this variable length, which in that we have the binary shift and Hoffman shift together, which arrange the source symbols in the accessing order of their probabilities and divide total number of symbols into the symbols block of equal size. Put the individual symbols in the block identically and add a special shift up and or shift down symbols to identify each block. There is one example here that even is from your book. You can see that the source symbol that we have in three different blocks with the concerned probability and binary codes that we have and different methods that it shows here. I don't want you just now to focus on that. We will work with this method meanwhile of MATLAB, but you should know the basic of that. And other method even can be the run length coding, which is that you will use the length of runs of ones and zero in a binary image, and through that you can specify the starting position and length of the runs of ones in each rounds of. And in type 2, and specify the length of run of in each row starting with the length of run. I show one example that it shows in the three rows of 1, 2, 3, and concern number it shows an relation which you can review uh, by this method, which can be higher again on the image. If I want to give you some provision about this idea, means that run length coding. This can be used for encoding using variable lengths, for example, of Huffman coding or for more compression. And we can have the accumulation between 0 to m for the variable k, and the formula that we shown here and the entropy associated with that, and average length runs of the zeros. And we can calculate for some h1 as the length of runs for the first, uh, and hence we have some approximation of the run length entropy. We can have the formula of HO and HL and LO and L1, which provides the average number of bits required to encode the run length. As we talked in the last lecture or so, this image compression is something, or it's we can say, with the uh, image point of view with respect to the data is something that like the data reduction process, that it can hire the different method and variable, which we will continue to talk more about this compression on the next lecture uh, also, and maybe we can finish these parts uh, with this week, and uh, start the new part, which is about the morphological part after that. But this is more important because somehow when you work with the image, you should think for comparison formats and also some data regarding that. Okay, for today, it's I think it's okay for us, because I want that you also review this point and to understand more about these compression methods. But we will talk more on the next lecture and also use the MATLAB with that to understand it better.